In this video, we're going to tackle single replacement reactions. I recognize a single replacement reaction as a single element reacting with a compound. So for example, I have a single element in zinc reacting with a compound, hydrogen chloride. Now here's the replacement part. Look what happens on the product side. Magically now zinc is with chlorine and hydrogen has been replaced. Look at this. It's as if zinc replaces hydrogen. So now zinc is with the chlorine. Hydrogen gets kicked out to be the single element. Elemental hydrogen is diatomic. Single replacements. A single element replaces an element that is already in a compound. In the second example, we have a single element in chlorine. And again, it's diatomic, but that's okay. It's not in a compound. And if I look at the product side, chlorine has now bonded to sodium. Chlorine must have replaced iodine. It's as if chlorine and iodine switch spots. A single replacement, a single element will replace an element that's already in a compound. Now there are a few rules before we can predict products of a single replacement. Not all single replacements work. You can't always go in the lab, mix things together, and expect some fabulous reaction. Sometimes nothing happens. So we're going to check a chart. It's called the Reactivity Series. You'll want to check this for all single replacement reactions. I will always give you the Reactivity Series. It's a list of elements in order of most reactive at the top to least reactive at the bottom. It looks something like this. So my top group of elements are my most reactive. My bottom elements are the least reactive, and this is their tendency to perform a single replacement reaction. Now some of this makes sense. The first category has a lot of alkali and alkaline earth metals. Well, those should be some of the most reactive elements. Then down toward the bottom, I have silver, platinum, and gold, which are virtually non-reactive. I wouldn't want jewelry made out of a highly reactive substance. Then the halogens are kind of pulled out separately, but the same rules apply. In a single replacement, fluorine is most likely to replace chlorine, bromine, or iodine. Iodine is least likely to perform a single replacement reaction. So the rule is, your single element must be more reactive than the one it's looking to replace. Or in other words, the single element needs to be higher on the reactivity series than the element it wants to replace. Okay, well that kind of makes sense. If I think about this first reaction, if zinc is going to kick out hydrogen and replace hydrogen, then zinc needs to be more reactive than hydrogen. If not, no reaction will occur. Same thing in the second example. Chlorine needs to be more reactive than iodine. And if not, no reaction will occur. So they kind of summarize that here. The single element must be more reactive than the one it's looking to replace. If not, it's a no reaction. So how do you know which elements are going to switch with each other? That's this rule. Only like-charged elements can switch. And by like-charged, we mean a positive element can switch another positive, a negative can switch another negative. So I like these examples. Zinc is most often +2. Hydrogen is +1. Chlorine is -1. So if zinc is a positive ion, it'll replace the other positive ion. It's okay that zinc is +2 and hydrogen is +1. That's fine. But it's positive for positive, negative for negative. So then I would need to make sure that zinc is more reactive than hydrogen. Or in the second example, sodium is +1. Iodine is -1. Chlorine is -1. So if my single element is normally negative, my single element, chlorine in this case, is looking to switch with the other negative, iodine. And so once we establish who's going to switch with who, that's where we check the reactivity series. And we make sure that is zinc more reactive than hydrogen? Yes. Is chlorine more reactive than iodine? Yes. Then those reactions will occur. We'll run a lot of these in the lab. We're going to run that zinc and HCl. We're going to run this one. Write the equation for the reaction of aluminum metal and copper 2 chloride solution. Now some people get good at these and they can predict what kind of a reaction will occur without even writing formulas. If you're not there yet, let's write some formulas. Aluminum metal, not diatomic, plus copper 2 chloride solution. So copper +2, chlorine -1. Okay, so now I might be able to recognize single replacement. I have a single element, aluminum, reacting with a compound, copper chloride. So to see if this works, I really need to check the charge of aluminum. Normally, aluminum would be a +3 ion. Since it's positive, aluminum is interested in switching with copper. Positive for positive. Then we just check the chart and see if that's okay. Aluminum, yes, is more reactive than copper. This is a go. So we switch our like charged elements, which means copper is going to get kicked out. Sorry, copper, you're on your own. Aluminum will come in. I'm going to kind of slide this over and bond with chlorine. Now again, that little subscript 2 by chlorine on the reactant side does not get a free ride to the product side. We needed 2 chlorine on the reactant side to balance the -2 of copper. But now if you make a new combination, we've got new charges. Now if chlorine is bonded with aluminum, I'm going to need 3 chlorine to make that compound neutral. Oh, so switch your elements, but then check those charges anytime you make a new compound. Now I get it, it's not balanced, but we can balance it. We're going to need to fix these chlorines, aren't we? I have 2 and 3, so I'm going to double this and go for 6. And I'll need 3 copper and 2 aluminum. And there we have it, it's balanced. If the formulas are written correctly, the balancing will be slick as snot. Now last thing we should do is put the phases in. We're going to run this reaction in the lab. You don't see that aluminum is a solid metal. A solution of copper chloride means that it's aqueous. Copper chloride is kind of a green crystalline solid. it's going to form kind of a green solution. On the product side, I would expect to form copper, which is a solid metal. The aluminum chloride will be aqueous. That's a solution. Now, when we run this in the lab, let's say we wanted to filter out the copper. So I set up my filter paper and my funnel. The solid copper would collect on the filter paper. Then you'll have this clear solution that drips through into your flask. That clear solution is the aluminum chloride. It's exactly what we're going to do in the lab. Oh. And don't freak out with the phases. In the upcoming videos, I will show you a chart that you can use to predict phase symbols if you're not running the reaction in the lab. That one is done. I love that reaction. Now what if you get something like the second one? Write the equation for the reaction of calcium metal and potassium nitrate solution. Alright, so calcium is not diatomic. Potassium nitrate. NO3. Potassium is +1. The nitrate ion is -1. And so now at this point I might recognize single replacement. My single element is calcium. It's reacting with a compound. If I glance at my periodic table, calcium normally forms +2 ions, which means that calcium is interested in replacing potassium. Positive for positive. So we check and see if that's okay. Calcium needs to be higher on this chart, or in other words, more reactive than potassium. They're both kind of up on the top. Here's potassium. Here's calcium. Calcium is less reactive than potassium, which means that this thing's not going to work. Essentially, this is a no reaction. You can abbreviate if you want. No reaction, this wouldn't work. Calcium would not be able to replace potassium. It's not reactive enough to kick out the potassium and form any new products. So when you recognize that, all you have to do is write no reaction. Cool. Well, those aren't so bad. And let's try one more. How about the reaction of fluorine gas and a solution of barium chloride? Okay, so fluorine gas, all the halogens are diatomic as elements. Barium chloride. +2, -1. I need 2 chlorine. So sometimes people kind of get on autopilot with these, and they assume that you always just switch with whatever element comes first. Not the case. Barium is +2, and fluorine would normally be -1. You can't switch oppositely charged ions. Fluorine is negative, so he's actually interested in switching with the chlorine. Here's what happens. Let's say by accident I switch fluorine and barium. Well, then I get a compound that's like fluorine and chlorine, and that's not likely to form. So you have to keep your ionic formula as one positive ion and one negative ion. Okay, so let's check our chart. Again, the halogens are kind of down at the bottom. Fluorine is more reactive than chlorine. This will work. Let's switch them. So on the product side, I'll have chlorine diatomic as an element, and then barium fluoride, +2 -1. I need 2 fluorine. Well, what do you know? It's balanced already. Excellent. And last thing I would do is put in my phases. Fluorine gas reacting with an aqueous solution of barium chloride. Chlorine is also a gas, kind of a yellowy toxic gas. Barium fluoride is an aqueous solution. I know you're so excited for this chart, right? Or if you're not witnessing the reaction in the lab, don't get your undies in a bundle. I can show you a shortcut on how to find phase symbols. But at this point, if you can use the reactivity series to predict a single replacement, you're in a good place. The single element will replace the one of like charge in the compound, positive for positive, negative for negative. Check the chart to make sure that the single element is more reactive than the one it's looking to replace. And if so, switch the elements, look for any other diatomic elements that might be formed, and watch your charges on any new compounds that might be formed.